My name is Dwayne Brown with the Office of Public Affairs, and welcome to NASA headquarters. The Cassini spacecraft continues to amaze scientists and reveal unprecedented findings and discoveries in the Saturn system. Today, scientists will share the latest and, quite frankly, surprising findings returned from the Cassini spacecraft. We'll have brief presentations, and then we will open it up for questions starting here at NASA headquarters and moving on to our NASA centers across the network. Let me introduce you to our participants. To my immediate left, Hunter Waite from the Southwest Research Institute in San Antonio, the principal investigator for the Ion and Neutral Mass Spectrometer. John Spencer, Southwest Research Institute in Boulder, Colorado, the co-investigator for the Composite Infrared Spectrometer. And Larry Esposito, University of Colorado Boulder, principal investigator, ultraviolet imaging spectrograph. And we'll start it off with Hunter.
Thank you, Dwayne. One of the most exciting discoveries of the Cassini-Huygens mission is the geysers of the small satellite Enceladus. Enceladus is about the size of the state of Arizona. Let me try to give you an idea of where Enceladus is within the Saturn system. If we can start with the first graphic, please. We show first the Saturn system, and then we zoom quickly to the E-ring that is Enceladus is embedded in, and then Enceladus with the plume at the bottom, southern hemisphere, and a zoom in of the plume and an animation. The plume is made of icy grains and gas as well. The icy grains are providing the scattered light that provides the image in this case. If we go on to the next graphic, we'll get an idea of the geometry of the flyby. In July this shows Enceladus once again, and the plume is shown in pseudo color to give you a perspective on things. If we go to the next graphic, you'll see the first flyby we made in March of 2005. This is the green era. We got fairly close to Enceladus. At the time of the planning, we did not know that Enceladus had a plume, so this was the discovery of the plume itself on this flyby. We were fairly lucky in getting close enough to see the plume and understand what was going on. And in the second graphic, once we knew the plume was there, we had the opportunity, going on to the next graphic, we had the opportunity to target this, particularly for getting very close to taste and smell the plume itself. The composition was the main thing that we were going for. You see, we came within 50 kilometers, quite close, and then we proceeded out along the plume axis. If we could go to the animation, you'll get a better idea of what that sequence looked like. Here we're coming in from the north in this sequence with the spacecraft. We'll get very close to the planet. We're moving in a direction to maximize the composition measurements during that flyby, pass by, and then on the way back out, we did the thermal infrared measurements with the composite infrared spectrometer. So these are the two important observations that were made. The plume shown in this particular graphic here was where we were really looking at the composition. And if we can transition from there to the first piece of data from the ion neutral mass spectrometer in the next figure, then you'll get an idea of how rapidly the rise in water density occurred as we moved over the plume. So you can see the density increase very dramatically as we moved over the plume. But water was not the only constituent that we saw. If we go on to the next graphic, we can get an idea of what the taste and smell of the plume. I said the line I used earlier was it's carbonated water with the essence of natural gas, which is not far from the facts in this case. Water vapor was the major constituent. There was methane present. There was carbon dioxide. There was carbon monoxide. There were simple organics, and there were more complex organics. The simple organics were composed of materials such as acetylene, hydrogen cyanide, formaldehyde, and ethane. The more complex organics included things such as propane, propyne, and acetonitrile. So those are the constituents we saw. Now, we try, the question that one would ask is, where did the organics come from? Of course, natural gas comes from decaying organic or biological matter on Earth, but this is not the conclusion we reach for Enceladus. Another possibility is the interior, the geochemistry going on in the interior. That can also produce organics. However, if we go to the next graphics, the simplest explanation is that the composition of the plume is very much like the composition of a comet. If we're looking at the abundance, and the different bars show the abundance level. So there was 90% water, there was a little bit of methane, there was carbon monoxide, carbon dioxide is shown here, and then the simple organics and the more complex organics. They're all shown with the bars and they're labeled. Then we show with the brackets what the composition, the variability in the composition of comets might be in the same situation. So we can see that it's quite similar to the comet composition. Finally, one would ask about the astrobiological potential. Does it, the fact that it looks like a comet, decrease our interest in the astrobiological potential? And the answer is absolutely no. Organics are one of the 3 ingredients that we need, or that we use as a measure of astrobiological potential. And the organics are clearly there in abundance beyond what we expected. In addition to that, one would be looking for liquid water and for a source of energy. And to discuss that aspect of things, I'll defer to John Spencer.
Thanks, Hunter. Yes, we've been looking at Enceladus in a very different way using the composite infrared spectrometer on board. And this looks at the surface of Enceladus and measures the temperatures and the heat radiation there. So the first graphic that I have shows the view of Enceladus we got the last time we flew past in 2005. And you see the thing that really blew us away when we first saw this is down at the South Pole. You have this very bright glow of heat coming out of the South Polar region. And if we go to the next graphic, we can put this in some context, because we also, with the Cassini cameras, got some pictures of the South Polar region during that flyby in 2005. And we see these 4 diagonal fractures, huge fractures, about 80 miles long, cutting across the South Polar region. And when you superimpose the heat map on top of that, on the right-hand side, you see that there is a lot of heat coming out from just that same area as where the fractures are. We saw temperatures as high as about -200 Fahrenheit, which sounds awfully cold, and it is, but the background temperature of the surface is less than -300 Fahrenheit. So these things really stood out as warm compared to that very cold background, and so it seemed like there was heat coming out of the interior of Enceladus. So on this new flyby, having made this discovery last time, we really wanted a closer look. And what we did is, from much closer to Enceladus, after Hunter made his measurements, we were able to scan that region inside the white box to see more detail. And the next graphic shows what we found. This is now the new data from that region inside the white box, showing now we see the heat coming out along each of those fractures individually. We see a great deal of detail here. We see a continual line of heat radiation along the fractures, but a lot of variation, some areas being much brighter than others. We see some areas that are not on these main tiger stripe fractures at all, but up in the right-hand corner, there's interesting other stuff going on. This is a beautiful map of where the action is on the south pole of Enceladus. Now, the composite infrared spectrometer doesn't just take images like this. We get a spectrum at every point, and that allows us to measure the temperature fairly precisely. And we just happened to get lucky that our best data was over the brightest tiger stripe. That's what we call these fractures, down in the lower right corner. And so there we were able to get a nice temperature measurement, and we saw temperatures as high as -135 degrees Fahrenheit, which again sounds pretty cold, but this is enormously higher than the background temperature, less than -300 Fahrenheit, and means we have a great deal of energy being delivered to the surface in this region. And so this is really interesting, because if we're seeing temperatures up to -135 degrees on the surface, we know it's going to be even warmer below that. And it's not out of the bounds of possibility that somewhere down below we're getting temperatures up approaching the temperature of liquid water. Whatever is producing this heat on the surface is going to be producing even more heat underneath. So we're not seeing liquid water or those temperatures, but everything we see, as the closer we look, the more energy we see, the higher temperatures we see, and it's entirely possible that there's going to be liquid water not too far below the surface of these warm fractures. Now, we have other data that we've taken recently with the Cassini cameras, which allows us to locate exactly where these geysers are coming out of. And the last graphic shows those locations. This is from previous work done by the Cassini imaging team, showing the main sources of the jets coming out of the South Pole, these geysers. And you see that there's quite a nice correlation with where the heat is coming out. The plumes tend to be coming out of the warmest points on the fractures. And so we're really beginning to get this very comprehensive picture. We have images of the surface to see the geology. We can see where the plumes are coming from. We can see where the heat is coming from. Other Cassini instruments are measuring the composition of the surface directly. But we have even more ways of observing the plume, and because there's so many wonderful instruments on Cassini that can look at the plume in so many different ways. And Larry Esposito will talk about some new results from another of the Cassini instruments.
Yes, thank you, John. So I'd like to talk about the results from the ultraviolet imaging spectrograph, and that sort of investigation is a little bit different from the previous two. Instead of going into the plume and measuring it as Hunter did, or looking at the surface and measuring that with a spectrometer, instead we watch a star as it passes behind the plume. And in the visual that you're seeing here, the horizontal green arrow shows the path of the star behind the plume. And as the star passes behind the plume, its starlight becomes dimmer, which allows us to measure the shape and the structure and also the composition of the plume. And as the star passes behind, we're able to turn this into a picture and a direct measurement of the environment of the plume very near the surface. So this is something that Cassini has not been able to do yet, to penetrate into the heart of the plume, which is measured by watching a star that passes behind. If we go to the next slide, we'll see an animation here. And this is an animation of what you would see from the Cassini spacecraft. That's the star Zeta Orionis, one of the stars in Orion's belt, passing behind the plumes there. And we need the audio for this, if we could turn the audio up on that. And as you see, the star dims as it passes behind each of the jets in the plume. That sound you're hearing is like a tea kettle. We're watching steam come out of the southern pole of Enceladus, and each of the jets, if we go back one more time for the animation, please. If we go back, please, to the animation. If we could step back to the animation. Thank you. So as the star Zeta Orionis passes behind, where the exiting gas is larger, the star dims, and we're able to measure, actually count the number of molecules along the path to the star. And so this gives us the most detailed measurements of the physical properties of the jets near the surface. And here's an artist's conception in this graphic of the jets coming off of the surface of Enceladus. The blue line with the arrow that proceeds from right to left is the path of the star as projected onto the surface of Enceladus. And each of those little letters, A, B, C, D, is one of the times that we see the dimming of the star increase that shows us the presence of a small jet coming off the surface of Enceladus. And as you can see from this visual, our observations A, B, C, and D roughly line up with the jets that have been observed by the cameras, the same ones that were indicated by stars in John Spencer's last visual. So there's a consistent story here that the cameras are seeing jets of gas lifting small grains of ice from the surface of Enceladus, and we are able to match those observations by watching a star that passes behind the moon. The next visual here is not of Enceladus, but of the Old Faithful geyser at Yellowstone. So this is the best analogy we have on the Earth to the phenomenon that's occurring on Enceladus. just like on Enceladus, water is shooting out of the surface of the moon. And there are, however, a few differences between Old Faithful, the geyser on the Earth, and the geysers that we're seeing on Enceladus. On Enceladus, there's no atmosphere. The sky is black, full of stars. The jets are continuous and not liquid water, but water vapor, essentially steam. And the particles entrained captured in that water are small grains of ice, about 1/10,000th of an inch across. And so now, with the combination of the direct measurements, the remote measurements, and the occultation by a star, we're getting a picture of the environment that's creating these jets on the surface of Enceladus. Water molecules ejected at over 1,000 miles per hour, carrying small grains of ice 1/10,000th of an inch across, shooting hundreds of kilometers above the surface of the moon Enceladus. Fortunately, this gas and the small particles are not a danger to Cassini, and therefore we'll be able to use the spacecraft to go yet closer to the moon and do yet more detailed investigations. We see on Enceladus the three basic requirements for the origin of life. We see water, although it may not be liquid. We see organic compounds detected by the ion and neutral mass spectrometer. And we also have a source of heat indicated by the composite infrared spectrometer. These three basic ingredients provide a minimum for the origin of life. Now, we don't yet see, nor can we tell or state whether the interior of Enceladus contains liquid water and if that water might be a habitat for life. But these are the questions that Cassini will focus on in our future flybys, the next of these in August, and then more in October and in the following years, to answer the question of what in the interior makes these jets and plumes which we see, and what connection that might be to a possible habitation for life. Thank you.
Thank you, gentlemen. Simply amazing stuff. Now, I know that we have a lot going on in the world of news today. I don't have any questions from our NASA centers. We have some folks here. Does anyone have a question for anyone? Seeing no hands, I want to remind folks that you can see this incredible data on www.nasa.gov, and want to remind you all that on April 3rd, we will start a series of briefings for the Mars Phoenix lander, scheduled to land on the red planet on May 25th. On April 3rd, we will start the briefing. Stay tuned for announcements on the time and location. I thank our participants again. Incredible news. Go to our website. And yes, you all know this. I say it and I mean it. Science never sleeps. Thanks for joining us.